And people send me questions. And by the way, you'll think of something on the way home. So by all means, just drop me an email and ask the question. And they don't all get in the column. About, I would say, less than 10% of them get in the column. I answer everybody's question personally within a few days, usually by email. And the ones that I think will be of interest to a lot of people, I tend to put in the column. But a lot of them are very specific about, how do I know which side of my radio is up and down, and that, things that not everybody would be interested in. I don't tend to put those in the column. So, but I get a lot of good questions, and there's no question that isn't a good question, of course. So with that, I guess I have a couple of caveats. I answer technical questions as best I can. There are other kinds of questions that I can attempt, but I'm not really the right guy for regulatory matters or ARL policy issues or pending legislation things, that kind of stuff. I don't do that. If you send me a question like that, I will forward it to the right person who will give you a proper answer. The other thing is, if I get questions at home, I can get a reference book, I can do antenna modeling, I can do transmission line modeling, or whatever it takes to come up with a good answer. If you ask me a question here, I give you the best answer I can, but while I can do some antenna modeling in my head, it works better if I use software, mostly. So with those caveats, what have we got in the way of questions?
Johnny, you want to start with yours?
Okay, my question is, what's the best way to use an oscilloscope to check that, I've got the correct modulation levels on my signal?
Well, an oscilloscope can be used to monitor the modulation envelope of the signal. And what you need, but that's really not the best way to find out what's happening, but it's a way, and it can be used. The trick is to get a sample of your signal after the last active stage. So out of your, if you have a linear amplifier, on the output of the linear.
Yeah, I built a little sampling port.
Okay, so you have a sampling port that puts out a signal that won't blow up your oscilloscope.
Yeah.
And it's good if it's sufficiently isolated so it doesn't generate harmonics, let's say, because typically what I would use would be a diode detector and a capacitor to eliminate the RF part of the signal and just look at the modulating envelope. And then what you can do is you can see that it increases smoothly with your voice level. And what you want to do is, one thing you want to do is put it on CW, put key down, and see what your full power level is, and line that up on the scope so that's in a couple of lines, top and the bottom of the screen. And what you want to make sure is that your voice modulation does not exceed or bump up against that level, because that's when you'll get clipping. So that can give you a good idea of what your modulation is doing. It should be smooth without any sharp breaks in the envelope anyplace. But the real best way to monitor or know what your signal is doing is look not in the time domain but in the frequency domain with a pan adapter. Now
I have a spectrum analyzer.
Okay, well, a spectrum analyzer will tell you more. And in setting things up, you can use a two-tone signal, two audio frequencies into your transmitter, equal amplitude. And what you should get out on the spectrum analyzer is two spikes of spectrum corresponding to the two signals you're putting in. If there's distortion, what typically happens is you get third order intermodulation distortion, for example, which gives you various sums and differences. And instead of seeing the two spikes, you'll see a whole bunch of them. And that's what makes people crazy, because they go into the next channel and interfere with other people. And it's a little harder to be sure about what's happening when you're talking into the mic, but you should be able to see the same thing, that the spectrum of your signal should be within kilohertz and a half either side of the center of your sideband filter. And if it's going out further than that, you're introducing distortion that's causing interference to other users. So
What frequencies would be optimal for the two-tones?
the two-tone should be within the sideband filter. So if you have a 2 kilohertz filter that has a bottom at 500 or 400 and a top at 2.4, you might want to have, I don't know, 400 hertz or 500 hertz and 1,000 hertz. Look, I'll do a Google search on two-tone generator, and there probably are some optimum frequencies for that. You probably don't want to have a 2-to-1 kind of thing, so you have the confusion of a harmonic.
You wouldn't be able
Yeah.
to figure them out.
But it's well established principles.
Thank you.
My pleasure.
Now, what about using the oscilloscope to check ESK or some of the other digitals? Would that be of use?
Well, the same kind of thing. You can see the waveforms, but of course you can't really tell exactly what's happening. I mean, it's again, in that case, you have alternating tones typically, or something. I'm not sure exactly what that would look like in the time domain, but again, in the frequency domain, it should look exactly like the two tones in the channel, and you shouldn't see other ones.
So if I'm over driving, I would see.
A bunch of other.
So that's the best way I can set my my audio level then.
I think that's true. Yeah.
Yeah.
I'm mostly a CW guy myself, so actually, one of the best ways is to look at the manual and do exactly what they say in terms of where the ALC meter goes when you talk and so forth. A lot of people make the mistake of saying, oh, I got a 100-watt transmitter, I'm looking at the power output. When I talk into it, it only shows 20 watts. I must need to turn things up a lot more. Well, the problem is the meter can't respond fast enough to your audio peaks. So unless you have a peak reading power meter, you're going to be, the readings on the meter are going to be much lower than what's actually happening. And actually a scope can give you a little bit of a reference about that because it will respond instantly. So, but usually if you follow the instructions in the transceiver manual and the amplifier manual too, so you don't overdrive that, everything will work just fine, in my experience. I guess not everybody writes good manuals. Sometimes the translators get the words backwards or something. But
Adam, you have some questions?
Yeah, did you forward the
Yeah.
question?
Why don't you give it to everybody?
Well, I gotta read that.
Okay.
He gotta read his own questions.
okay. If it's one he sent me, I'll read the answer.
I have two questions. One of the question was a friend of mine. He has 2 elements delta loop on the top of the flat roof.
Yeah, that's not a dry erase, so.
This board isn't?
No, the pen in your hand is not dry erase, so.
Oh, it says permanent, doesn't it? Yeah.
Right,
I was-
we'll just never get it on.
I tested it with my finger. It seemed to work. If we do have it,
That's what I was looking for the dry erase. I can't find any dry erase. Wait a minute, is this one? Sharpie flip chart, no.
If I read the instructions, I would have known.
Somebody took all of the dry erase markers out of here.
I don't usually use that, but it occurred to me that talking about antenna stuff, a picture might work.
I'm smart, I would have moved that table.
Here's some paper, it's permanent.
Well, I probably don't need it.
There you go.
Thank you. Okay, so the question is, what is the effect of the antenna on the roof? And the two choices.
You want to draw something?
Oh, thank you.
Okay, so basically, yeah,
Yeah.
he has a 2 elements delta loop on the top of the flat roof.
That's a little bigger.
135 feet above the ground. And the question was like, who is affecting his performance of his antenna? And is he better off, having the same, antenna, let's say, on a 70 feet, tower above the ground?
Okay, so the question really is, here we have a 150-foot high structure including a tower. Top 20 feet of it is a tower on top of a flat roof. And the question is the antenna better off 20 feet above the tower? Really what you're saying is it as if I have an antenna 20 feet off the ground, or is it an antenna 155 feet off the ground? Good question. Well, a lot of it depends on the extent of the roof and what the roof is made of. But just to give you some numbers, I modeled this afternoon, so I got the note, and it didn't say what band it was on. I assumed it was on 20 meters. And if it's at 155 feet without a flat roof, just in free space, we have a 155-foot tower, we wish, right? The gain of this antenna, 2-element delta loop, would be 11.8 dBi with a peak elevation angle of 6 degrees. That's pretty nice, because that gets you nice low angle coverage, which is what you want for DX. Now, what about if it were not on a building and at 60 feet was your other choice? Well, that gives you about the same gain as you would expect, actually 11.5, but the peak elevation angle is now 13 degrees, which is not terrible, and in fact in many cases that's fine, because it's not all going there, it's going over a fairly wide angular region. But I'd take this over that any time. Now the question is, okay, what does the roof do? Well, when you're talking a signal at 6 degrees, that signal is combined, the forward lobe combined with the reflected lobe. The reflection happens far out away from where the antenna is. So unless the roof goes out, and I could have done this geometrically, but I didn't, probably a quarter mile, it's not going to have much of an effect. But to see what effect it would have, what I did was I built a little grid of on 6-foot center, 6-foot square screen, if you would, 48 feet on a side, just because I got tired of copying all my line segments over and over again. And what I found was with that, it actually, with the roof, that model of a roof, it was actually 12.8 dBi. So somehow I actually got additional gain, and still at 6 degrees. Now I think, in looking at the plots, with the roof right here, I did get more kind of high angle clutter due to reflections from the roof, but it wasn't dramatic. So my answer was, unless the roof goes out a long way, that's a really great situation. And I would have thought a metal roof would be the worst possible thing to have there, because if it's wooden, it will hardly be noticeable. But even though this metal structure, at a 6-foot square, each side is about 1/10 of a wavelength on 20 meters. So that should act about like a solid metal sheet in terms of the reflective properties. So it really doesn't hurt. It actually improves the signal. So don't get rid of the building. Keep the building. That's my answer to that.
So the roof would also shield the people underneath?
Well, that's true too. Well, again, depending on what it's made of.
If it's a metal roof, if
Yeah.
it was beams.
Yeah, now of course if it's a wooden roof and you've got a bunch of wiring underneath and it's carrying noisy signals, that's not necessarily to the good. But again, not knowing all that, it's hard to figure these things. But just based on the roof itself, it looks like it's either wouldn't do anything or it would do very little.
If you had a wire, say a short wire, parallel to one of the elements of the antenna embedded in that roof, would that act as a parasitic element?
Well, of course, these wires were extended out 48 feet, and they were, it happens that they were parallel to the, just because of the way I oriented things. And parallel will have an effect, but it's not great if it isn't resonant. In other words, if it isn't a multiple of a half wavelength, it's not going to absorb and re-radiate a lot of energy. So it could have some effect, but again, you'd have to model it to find out.
So, I'm thinking of a situation with some of the National Guard armories where they've got dipoles strung about 25 feet above their roofs. The roofs are slate, probably a lot of metal underneath them. It almost sounds like those roofs would not have much of an impact on their...
I think that's probably true. Now, you will get a little more, you know, the roofs will tend to, the close-in stuff will tend to reflect at high angles. So you will get more high-angle radiation than you might without the roofs, but you won't get a lot less going off other directions. And for their purposes, it actually may be beneficial to get NVIS kind of coverage.
Yeah, they're down here in Connecticut, they're mostly talking to Fort Drum, which is in western New York.
Yeah.
So the radiation, you know, the below angle stuff isn't bad, but the NVIS is also a good thing. You know?
Yeah.
Okay, good. Thank you. And Adam had a second.
Yeah, and there was a second question about 12-element Yagi for 80 meters, okay, installed at 75 feet. Does it make any sense to put another, 2-element, let's say, at 35 feet, which is going to be lower, and in phase? Is that going to make any gain? And is it going to be, is it connecting in phase those two elements, it's going to change the takeoff angle?
Yes, but it changes it in a way you don't want, actually. And think about it, if we talk about, by the way, 2-element Yagi for 80 meters that's 75 feet off the ground is not bad, even though it's a low height for a Yagi. It's about a little more than a quarter wavelength. It still has a benefit of bringing the signal down to relatively low angles, not very low, but there's more low angle energy than there would be if it were a single element antenna, and there's less going straight up, so less NVIS and more going out in the direction you want, but of course it's not down near the horizon, but it's still, there's more energy at the horizon than there would be without it. I ran that model too. And I'll start with a slightly different discussion, which is why would you, what about stacking Yagis? Well, let's think about it for a minute. In order to stack a Yagi, what you're doing is you're taking two Yagis and you're dividing the power between them and transmitting them in phase, so they add, hopefully at the angle of their, the angle away from them, what's the word I'm struggling with?
You call it takeoff angle?
The takeoff angle is, so if you look at the side of them, what you want to do is you want to have, by feeding them in phase, you're trying to send the energy down in this direction. You're feeding these two antennas, these are end views of the antennas, you're feeding them in phase. You're getting maximum effect perpendicular to the plane of the antennas. That's what you want. Now, the problem, of course, is you have the ground down here also entering in, and that tends to cancel radiation along the horizon, so it will be somewhat higher, but it can be better than just having a single antenna. The problem is the antennas have to be far enough apart so they kind of have independent effect on the signals. If the antennas are in the same place, it just acts like one thick antenna, right? And so, does that make sense? In other words, you have two antennas in phase and they're 2 inches apart. It'll just act like one antenna that's 2 inches thick, right? So you have to get them pretty far apart to make it work. So how far apart does it have to be? Well, this antenna is about a half wave above ground, and you're talking about putting one sort of part way down from that. Well, that's not going to work. I'll give you the numbers about that. But what can work is if we say we have an antenna at a half a wave height, and what did I run here? If we had that same, this is a 2-element Yagi, the 2-element Yagi by itself has about 9.4 dBi gain. at a takeoff angle of 41 degrees. Now that's pretty high for DX work, but what might be of interest is at 10 degrees, it still has some signal, and it has 1.6 dBi. Now that's probably 3 dB higher than somebody's quarter wave vertical, let's say. So it's not a bad antenna for DX, it's just not a great antenna. Be much better if you could have it on a 150-foot tower, have it on top of this roof, would work much better. But, so what if you wanted to phase this with another one? If you made, if you had one at, wish I could read my writing. Okay, 75 and 40. Well, let's look at that case with the other antenna down here. 40 feet up, 35 feet below the other one. That's a spacing of an eighth of a wavelength, roughly. You actually get 8.9 dBi gain, a dB, or half a dB less gain, and the elevation angle is higher. So it does everything you don't want to do. That other antenna is not far enough apart, and it needs to be higher. If you had it up on this side of it, if you got a, suddenly grew a bunch of trees and had one at, let's say, 215 feet, which would be a half a wavelength above this one. That's a fairly normal spacing for stacked antennas, is a half wavelength spacing. Now we're talking, you'd get 12.8 dB gain, so about more than 3 dB additional gain, and the elevation angle is now at 20 degrees. And at 10 degrees, you'd have 10 dBi of gain. So, big difference. So you put that antenna above this one with a half wavelength spacing, you get a real boost in performance. You put it down here, it tends to do everything you don't want it to do. So you've really got to go up, and you've got to go further apart. If you just separated it by a quarter wavelength, so you had it at 75 and 145, it's a little bit better. It gives you 10.9 dB gain at 29 degrees. So again, that's about 1.5 dB additional gain. And it's a little bit lower than this one at 75, but it's not a big difference. So you really have to get on the order of a half wavelength apart to make a difference, and you really want to get higher. Does that make sense? Okay. So, but this thing about making wire, oh, you know what I did? Another thing I did, I said, well, you know, if you're going to go, you want to do something with this antenna, make it better, what about adding a third element, make it a 3-element Yagi? Ah, here we are. Okay. That gives you about an additional half a dB gain. So this is not going any higher, just adding a third element, make it a 3-element Yagi with a reflector and a director, and you get 10.2 dB gain at 39 degrees. So it gives you a dB and a half additional gain, and it brings it down a few degrees. So for one piece of wire, you actually get an improvement with that, as opposed to having another 2-element Yagi below it, which makes things worse. So use your wire where it's going to do the most good, I guess is the answer. Does that make sense? Okay. Other questions?
Can I just ask a quick follow-up question?
Sure.
It goes in a different direction entirely, though. I have access to a site where I could actually get a wire beam for 80 up at approximately 90 feet.
Yeah.
You know, I was wondering whether it was worth the effort, but based on what I've heard here now, it would be.
Oh, absolutely. Yeah, because that's somewhat higher than this.
Right.
And what you do, I mean, the pattern of it, if you had a dipole at 90 feet,
Right.
that's a little more than, that's about 3/8 of a wavelength.
Right. I was thinking that the minimum.
Yeah.
Right.
So what's its pattern look like? If you look at this is the end view of the antenna. If you look at the pattern, it's going to mostly be going up.
Sure.
Anything less than a half wavelength is predominantly going up. You make a 2-element beam out of that, and instead of going up, what you'll find is it'll start to go like that.
Sure.
Now, this is not a real low angle, but what happens is at the very low angles, you have more with this than you would with the dipole. So it makes a difference, and 3 elements makes it even better, and 5 is even better.
I've never considered that aspect,
Yeah.
having a parasitic, to the extent that it would affect the take-on angle. It just never occurred to me that.
Yeah,
Totally new.
it's
Spacing.
yeah.
I'm doing 80 meter wire beam, but actually for 75, DX window at around 3,800. 1/8 wavelength spacing between the 2 elements.
Well,
What do you think? Does it work out?
what I would like to do is if you send me that question,
I'll do that, sure.
I'll actually model it. But
I didn't expect this off the cuff.
yeah, well, what I did here is I took a 50-foot spacing for each parasitic element, which is let's see, what did I say? It's about 0.15
Yeah, that's
wavelength, something like that, which is fairly typical for a small beam, and not that there's a small beam on 80 meters, but I figured you probably wouldn't want a great big thing.
Right.
And I can, if you give me the constraints that you have on where you can put the elements and how many you want to do, I can do a little futzing around and come up with some dimensions for you.
What I would try to imitate is we use a wire beam for field tech that we worked out a very interesting configuration for by assembling using surplus elements from donated beams that will never be resuscitated. We have managed to build spreaders.
I've been using a beam like that for many years.
Yes. Right. And so the thing is now on the wire beams for 40 we've experienced with 13 feet, worked out quite well. There's also another sort of support for 17 to 18 feet as the spacing.
Yeah.
So I'm just wondering, can I get away with approximate 34, 35 foot spacing on the 80 meter beam and still get some productive results?
I'm sure you can get some productive results. I mean, not necessarily obviously, but the wider spacing will give you more gain and wider bandwidth and probably a higher feed impedance.
Sure.
But smaller spacings work, they have for years, and but we can find out. I can give you the numbers and show you exactly what you get for the different choices that you have to make. But it really is, it's a very, I actually answered this question in QST some time ago from somebody who was going to Nova Scotia and doing something. Now, of course, the downside of it is it's very hard to rotate one of those. So you either have to have some particular clump of people you want to talk to, or a bunch of them, or some other antenna to use for other purposes. So I mean, that's the one downside of this. But given that, if you know you want to head towards Europe or whatever, while I was doing this, I was thinking about it. I'm struggling to get my 5-band DXCC before my 80-meter antenna falls down, which is starting to fray. The halyard is starting to fray. I don't know quite what I'm going to do with it next. And I'm up to about 95 countries. I got the other 4 bands, so I've got to. But if I had that beam, I could probably knock them out. And I have to stop watching TV at night, play radio.
Apropos Terry's antenna discussion.
The co-builder of the wire beams.
Have you given any thought to how you would suspend a 2-element 80-meter wire yagi? With this, we worked out a way of getting everything nice and parallel with a 2-point suspension with a 40-meter yagi.
Yep.
But 80 meters, you really need to have 4 mount point, 5 points.
Well,
I'm not so sure that we've done
one
that.
thing to think about is consider an inverted V in which you just have the ridge pole out of rope. Then you just need 2 supports, and you can come. Now, inverted V's give you a little less performance for the height than a dipole, but not a lot. And if you don't have, it's much faster than waiting for the trees to grow. So,
I've read
Not to be
articles.
too militant, that's his idea.
oh, I see.
My critique has been it's trash.
Oh. By the way, let me write down my email address.
Right.
I have a number of them, but this is the one you want to use.
All right, yeah, we'll definitely send you something, because that would be very
And it
nice.
has to, the org is important. If I mean, my personal email is on my QRZ site, and w1zr@arl.net goes to that. The problem is I get so much junk email, unless I know what it is, it's out. But if it comes to this arl.org, it's a whole different system, and it's most all related to what I'm supposed to be doing. So I don't lose it. So So use this address as a preferred address. Okay.
Just understand that knowing Terry, he's probably thinking of a helicopter to hold up this.
Yeah, if we
Well-
get away with it, I'd do it.
Well, think drones.
We have.
So what you just said, I'm just kind of, having another question. The first antenna, okay, having on a building. So basically, my understanding of any antenna, dipole, Yagi, inverted B, whatever, basically is, the principle is whatever the antenna can see. So if its antenna is going to be on the cliff, right?
Yep.
That extra, height of the cliff, it's going to get you the better, takeoff.
Right.
So basically, whatever the height of the antenna on that cliff, plus additional feet, above the above the true ground, right?
That's pretty much the case. I mean, it's getting kind of busy. Maybe I can.
Yeah. Because what I just want to mention, friend Terry, he was with me and he was helping me put 80 meters dipole. And 80 meters dipole, you put, let's say, roughly about 65, 70 feet, but it's on the cliff. And the cliff goes another, I don't know, 100 feet, maybe 150 feet.
And slopes off towards Europe.
And this dipole, I mean, I can run, 10 watts and I'll be getting a contacts with Europe, no problem. It's really working well. I mean, South Georgia, that was easy. This dipole. I mean, I was really surprised, but it's.
I couldn't hear them on 80.
Well, I mean, I made a contact on the side.
Wow. Yeah, here's what happens. Now think about it. When your antenna left to it's looking again at the end of an antenna, the antenna by itself will radiate all the way around the axis of the antenna, right? In general. Now, what happens is if you put another surface here somewhere, what will happen is you'll get reflections. But notice that the reflections here go off at fairly high angles. If you're talking about something happening at low angles, that's a reflection that happens far, far away from the antenna. So that this is, a step function here. This can go out quite a ways before it interferes with the signals that'll reflect and add in at low angles. So, I mean, it just, this is not necessarily good, and you really want all your energy to go at the low angles, but if you have to lose some going up, that's not too bad. Of course, the problem with that is noise tends to be fairly local and tends to be NVIS-like and comes in from the high angle. So you will get some negative effects of having this building here, but as far as getting your signal out to the distances, I think unless the building is very, very large, you're on the wrong end of an aircraft carrier, it's not going to be a problem. People tend to confuse ground effects. There are different ones that happen right at the base of a monopole, for example, which contribute to how much energy you put into the antenna, but that's completely separate from the reflective properties of the Earth that happen at some distance from the antenna.
I've got a theoretical situation. Well, first I want to ask, how would a dipole antenna pitched, strung just below the roof peak of a top floor apartment perform? And would it present a hazard to the people in the apartment?
Well, the first thing you have to know about is what the construction of the roof is.
Wood.
Yeah, if it's wood and there's not a bunch of wire, heating ducts right under it or wiring right around it, it will work reasonably well, but not nearly as well as it would if it were on the other side of the roof. I mean, the roof is going to absorb a little bit, but it'll work. If that's what you have to do, it'll work. A lot of people do that. Is it a hazard? You have to do your RF safety assessment. And it's a question of how far it is from the antenna to the people and how much power you're running and what frequency you're doing it on. And there are tables and so forth you can use to find out about that. Generally on HF with reasonable powers, it's not too much of a problem until you get up at the high end, 10 meters and so forth. You have to be a little more careful,
Reasonable power, you mean like 100 watts?
or less, yeah.
Yeah, except 10 meters would have to be.
Well, yeah, there's actually an exception up to, I think, up through 15 meters. You don't have to even do an assessment for, it's different for each band, but 100 watts is clear up through, I think, 15 meters, and then you have to be a little less at 12 and 10 meters. At VHF, more of a problem because the energy tends to be more concentrated. But I still think if you have an antenna in a house or right near people, you probably should do a more detailed assessment and find out what's really going to happen. But it's not, you know, if you don't do something really dumb, it's not a problem. You run a
Watch
kilowatt.
out for the gutter.
Pardon me?
If there's a gutter for the
Yeah, well, the gutters can have, again, a horizontal structure that is not resonant is not going to have a great deal of effect, particularly if it is shorter than a half wavelength. But the problems you can get into is bad joints in gutters that act like semiconductors and generate harmonics, which are not as much of a problem as they used to be before cable TV. But people used to have problems with that sort of thing. So that's an issue. I'm more concerned about somebody who lives in an apartment building that has a fire or security alarm system with wires running all over the place. And you hit the key, and before you know it, you got fire trucks and police cars all over the place.
I have about 20 or 30 ferrite beads on my burglar alarm.
I see. I'm sure that impresses the burglars.
Well, they're all in the basement with my transmitter. So.
Yeah.
Actually, I have enough room. You see, it's a shotgun apartment. I have enough room to string a 20-meter dipole completely indoors. If I'm half in, half out, I could go to 80 meters with something like that. I'm just, you know, just a little confused and wondering if the wood structure would kill a lot of the signal.
I don't think wood kills a lot of signal. I mean, trees don't. We put antennas in woods and they get out. I have trees all over the place.
Yeah, and this is going to be about 30 feet above ground.
That's a reasonable height for a 20-meter dipole, and
Yeah.
it'll work reasonably well. I think. I mean, try it, and if it doesn't work, try something else.
Okay,
Sir?
You keep mentioning
Thanks.
material for roofs. One roof that I've experienced is an EPDM roof. It's kind of rubber roof, vulcanized tire roof.
Huh.
Do you have any experience with that?
Never even heard of it. But I think that's a dielectric material. I wouldn't think it would be that much different than insulation on wires or anything else. I mean, the thing you got to watch out for is some insulation is foil backed. If you have foil, you know, the whole roof is covered with foil, you're not going to get a signal through that, I don't think. But that's the main thing.
So rubber should.
I wouldn't think rubber would be a problem.
Just a follow-up question. You mentioned MDIS a few times during the presentation. Just a broad question. What's any thoughts on some of the new research out there, or any new studies that we should know about on MDIS?
Well, I don't know of any particular studies other than the fact it's been used very successfully. It's something that really came up during the Balkan Wars. Prior to that, most military short-range communication was on VHF, and similar to VHF FM kinds of things. And that works great if you're in flat terrain or if you have repeaters. And of course, to have a repeater, you have to own the mountaintop or hold the mountaintop. And that's not the way the fighting was in the Balkans. We didn't hold positions. There were mountains all over the place. And I don't know whether it was accidental or how they found out that HF, using the existing HF equipment, could work very well for short range, high angle, if you went to horizontal antennas. So all of a sudden, all the whips that they have, big whips on the back of their vehicles that used to be standing straight up, they all had clips on them so you could get through tunnels and things. If you just left them down that way, it worked great. And NVIS was born. And I think that it's kind of an amazing story if you think about it. You know, I don't think there was a giant amount of government research. There may have been, but the solutions were so straightforward. And of course, everybody then made custom NVIS antennas and so forth. But particularly on 80 and 40 meters, unless you have a very tall tower, that's what you got is an NVIS antenna, even if you don't want it.
There was an article in QST a year or two ago, and it had the unfortunate title about a myth, the myth of NVIS, and the myth he was talking about was that the antenna should be very, very low to the ground.
Yeah.
But the author was suggesting for 80 meters at about 60 feet, call it about a quarter wavelength.
Quarter wavelength.
So that a quarter wavelength is the best spot for the antenna, whatever frequency you're on, quarter wavelength.
Quarter wavelength is very good because if you look at the elevation pattern, it's mostly going straight up. And and once you get beyond that, in fact, you can go almost to a half wavelength before you start having a null. At a half wave, you have a null going up. Below a half wavelength, you don't. And the other nice thing about a quarter wavelength is it's relatively easy to match. As you get down real low, in addition to tripping people and trapping lawnmowers and so forth, snaring deer, you have a less efficiency, and typically the antenna feed impedance is much lower, depending on the ground conductivity. So it's harder to match, less efficient, and so forth. On the other hand, it's a lot easier to put up an antenna at 10 feet above the ground than it is to put one up 70 feet in the ground if you're on a, if you're on a temporary situation. What I really like, my favorite, is to get one of these 40-foot expanding fiberglass poles, put an 80-meter inverted V as guy wires going one way, and a 40-meter inverted V going the other way, put them in parallel, and they'll work much better than most parallel dipoles, which don't work because they're usually coupled too close. And those are the two bands you want for NVIS, and you can set it up in 10 minutes, and off you go. So that's, and at 40 feet, it's just about the optimum height for both bands. So
the rule of thumb is quarter wavelength high. What is the length of the horizontal?
Well, whatever it takes to match the antenna. Half wavelength doesn't require anything dramatic. You just hook a feed line in the middle. Other lengths will work, but you need loading coils or something to make it work. So typical half-wave dipole. And the interesting thing about it is we think of a half-wave dipole as having a two-directional pattern with nulls off the end. As the antenna gets low to NVIS heights, it no longer has nulls. It's a little less intense off the ends, but instead of being down 25 dB off the ends, it might be down 8 dB off the ends. So you get omnidirectional, virtually or functionally omnidirectional coverage, which is just what you want usually for NVIS as well. So it gives you the kind of omnidirectional performance you thought you had to get a vertical for, and but yet it works over mountains.
I have a vertical, and I have a wall right behind it. I mean, there's a driveway that goes behind my house. So it faces, essentially, I can pick up Europe quite well. I can pick up north and south, but the west is a rare contact.
Uh-huh.
But it's a Hustler 5-band
Right.
vertical. And the big advantage of it is that when the hemlocks come crashing down, they don't take down all my wires. So I've given up. I've kind of given up on the wires. The Wyndhams and all that I've put up 3 or 4 times, and I got my neighbor to cut down a bunch of these